Hello my beautiful PU1 students. So I know it's a very hectic time for you people because FA2 exam is knocking the door, right? So yeah, in this particular condition I am here to help you out by giving you the most probable questions that you are going to face in your upcoming examination. So here in this particular session I am going to cover 3 chapters. That is the most important one, and definitely it includes your syllabus. The first one is the equilibrium, the second one is the redox, and the third one is the hydrocarbon. So these are gonna be the most probable questions that you are going to face it. And I am also going to give you the detailed explanation video and some tips, some tricks, some numerical problem from the equilibrium chapter as well. So stay tuned, let's get started. Make sure that you are watching till end, otherwise you're gonna miss it. Okay, so let's proceed. First we are going to proceed with the equilibrium chapter. Okay, so first we will proceed with some MCQ questions. So whenever it comes to the MCQ, you can see what effect does a catalyst have on the equilibrium position of a reaction. Always remember that catalyst, there is a tendency for a student whenever they are seeing that catalyst, okay, it makes the reaction rate faster, or it makes the reaction faster and it gives more product. There is a tendency to do like that. You can see a catalyst favors the formation of products. First option is something like that. But let me tell you, my dear, catalyst, it helps whenever the reaction is in equilibrium. It doesn't affect the equilibrium condition. So what is the role of catalyst? Catalyst helps the reaction to reach the equilibrium condition in a faster way. Okay, means after once it attains the equilibrium, then there will be no role of the catalyst, right? So you can see here the correct option is going to be C. So catalyst does not change the equilibrium position of a reaction, rather it helps to attain the equilibrium faster. Okay, let's proceed the next one. Which of the following statement is incorrect? Adding the products shift the reaction to the left means it's towards the reactant end. So definitely in accordance to the Le Chatelier principle, if you keep adding more and more product, then there will be disbalanced, there will be more number of product, less number of reactants, right? So to achieve the equilibrium condition, definitely the reaction will be shifted to the left. So definitely it's going to be a correct one, but they are asking for the incorrect. Let's see. Adding the reaction shifts, adding the reactants shift the equilibrium to the right. So that's also going to be the correct one, because whenever you are adding more number of reactants, so there will be disbalanced, right? More number of reactant and less number of product. So to minimize this phenomenon, this disbalance or this disturbed in equilibrium, some amount of extra reactant will go towards the product. So towards product means it's towards right. So that's also correct one. Now you can see exothermic reaction shift the equilibrium to the left with increasing the temperature. So whenever it comes to the matter of the exothermic reaction means it releases heat, right? It releases heat. So whenever a reaction releases heat, again you are increasing temperature in that particular case. So in those cases, reaction tries to utilizes the extra temperature. Always remember, if for an equilibrium reaction, forward process is exothermic, backward reaction is definitely endothermic. So the reaction will utilize the excess temperature by proceeding the reaction towards backward. Okay, so definitely this is also the correct. So adding a catalyst shifts the reactant to the right. No, it's gonna be the wrong one, because as I told you in the last slide that catalyst has no role to shift the equilibrium. It only helps in achieving the equilibrium. Okay, so definitely this is gonna be the correct answer. Okay, let's proceed further. For the reaction of hydrogen cyanide with water to form hydrogen ions and cyanide ions, the equilibrium constant is that. What does this tell you about the position of the equilibrium? So as you can see, the value is really very less, right? The value is really very less because 10 power minus 10. So let's look at the option. The equilibrium lies towards the reactant and the rate is low. Definitely by default you can get that this is the correct answer. Why? Because you can see the value is very less and there is a range of the value of equilibrium constant where it tells that whenever the value is very less, means below 10 power minus 3, then hardly the reaction will proceed towards the product. So definitely it will lie towards the reactant end and the reaction is very slow. Okay, let's proceed. Here you can see conjugate base for the Bronsted acid H2O and HF. What is conjugate base? Conjugate base is acid after releasing its acidic hydrogen. Okay, acid after releasing its acidic hydrogen, whatever it will come, that is called conjugate base. So I am having H2O, right? I'm having H2O here. So H2O, if it releases H plus, H2O if it releases H plus, OH minus will be there. So OH minus is the CB or conjugate base. And if you are having HF, if it releases H plus plus F minus, so F minus is the CB. So definitely this is gonna be the correct answer. Okay, let's proceed further. Okay, let's proceed for the next question. You can see the question is, which of the following fluorocompound is most likely to behave as a Lewis base? Lewis base means what? When it donates lone pair in the medium, right? Donates lone pair. So lone pair donation means it must have excess lone pair to be donated. Okay, so when there is a chance to having extra lone pair, when the particular central atom is electronegative in nature. But if you just look at this particular case, BF3, boron is electropositive in nature. Phosphorus, it is having the lone pair, okay, because it comes in the series of nitrogen then phosphorus. So definitely phosphorus is also having lone pair. And carbon is not having lone pair, silicon is also not having lone pair. So BF3 is the option. Now look at that, which of the following pairs of solution is not an acidic buffer? Acidic buffer is what? Acidic buffer means the combination of the weak acid and its conjugate base. Okay, let's take a weak acid like CH3COOH. If I take the conjugate base of this CH3COO minus, I need this type of composition. Okay, weak acid plus its conjugate base. Okay, so you can see for the first case, you can see the combination CH3COOH and CH3COONA. This particular salt will give you this particular ion, right? Now if you just look at H2CO3 and Na2CO3, H2CO3 is also a weak acid and CO3 2 minus, that is also the conjugate base of it. H3PO4 and Na2PO4 for the same case, but look at that HClO4 and NaClO4. HClO4 is a strong acid, right? So this is going to be the wrong answer. Okay, means it's not an acidic buffer. Okay, it's a strong acid and its conjugate base. Got it? Let's proceed further. Okay, so we are entering into the fill in the blanks. Okay, fill in the blanks type of question. If the value of an equilibrium constant for a particular reaction is this, then the equilibrium then at equilibrium the system will contain mostly, see, if you see the value 10 power 12, very high value. Okay, there is a range of K I told you. If it is like above 10 cube, then it is very much towards the product. Okay, means the reaction will be almost about to be completed. Okay, so you can see here, you can see the answer should be the product. Okay, let's proceed further. Okay, next is dash of 0.01 molar sodium hydroxide is, okay, so here you can see you have to find the POH, I guess, okay, POH for this particular case. Okay, so if you just simply find out the POH of sodium hydroxide, POH is minus log of concentration of OH minus, right? So here you can see minus log of 1 by 10 power 1 by 100, right? 1 by 100. So minus log of 10 power minus 2. So from here I am getting 2. So your value is going to be the 2. Okay, you have to find the POH for this case. Okay, let's proceed further. Okay, so now we are entering into the 2 marker question. So here actually comes the mention any 2 application of the equilibrium constant. Here you can see I have written 3 actual application. As it is a 2 marker question, you don't have to explain that much. Just write first the predict, means if you just look at the value of K, then you will understand if the reaction will be towards the product end or towards the reactant end, or the reaction will be completed or not. You can see that's the first thing. Predict the direction of the reaction. Okay, predict the extent of reaction, means up to which extent I will get the product, up to which extent I am going to get the reactant, like that. Okay, and the calculating the equilibrium concentration of the reactants and products. So as you can see, how I represent the K equals to product. Let's say if I am having this type of reaction, right? So from here product by reactant, stoichiometry will go to the power, right? This is how we write. So if you are having this value na, then you can get the concentration value of, the product and reactant, right? So these are the 3 application of the equilibrium constant. Next question, consider the reaction. How would the equilibrium be affected by first addition of Cl2, next is decrease in the volume of the container. See, first one by one I am telling. So if I add Cl2, addition of Cl2, it means it indicates addition of Cl2 increases, more number of product number will be increasing, right? So if product number increases, then there will be a disbalance in the equilibrium. There will be more number of product, less number of reactant, right? So in accordance to the Le-Chatelier principle, it will try to minimize this disruption, right? And hence the reaction will be shifted towards reactants. Okay, so what you have to write, simply on addition of Cl2 there will be more number of product and it will cause some disruption in the equilibrium. As a result of this, in accordance to the Le-Chatelier principle, the reaction will be shifted towards the reactant end. That's it. Okay, next point whatever they are asking, see, decrease in the volume of the container. So if you decrease the volume, what will happen? How pressure and volume is related, you imagine. If you decrease volume, pressure increases, because pressure is inversely proportional to V, right? So if pressure is increased, now you imagine the effect of pressure. What is the effect of pressure? Listen carefully. If the pressure of a system is increased, pressure of the container in which the equilibrium is achieved, that pressure if it is increased, then the reaction will be shifted towards that end where there are less number of molecules, right? More pressure, right? You have to minimize the pressure. So where it will go? That direction where there are less number of molecules. Okay, so now pressure is increased. Now you can see here I am having 2 molecules, here I am having 1 molecule, right? Here I am having 1 molecule. So the reaction will be shifted towards the reactant end. Okay, so if pressure is increased, then what happens basically? Reaction will be shifted in a direction where there are less number of molecules. Hence, for this particular case, it will be shifted towards reactant. Right? I guess you understood what's the reason behind it. Let's proceed further. Okay, give the equilibrium constant expression for this thing, and if helium gas is injected. Okay, first let's write the equilibrium constant. You know this basically equals to product by reactant, right? So product is NH3 and the stoichiometry goes to the power. Okay, here into H2 whole cube. Okay, I guess you understood this. Let's proceed towards the next part. If helium gas is injected into the vessel without disturbing the overall pressure of the system, what will be the effect on the equilibrium? So basically, whenever you are without disrupting the pressure, you are injecting some other gas molecule, right? You are adding helium in the system. So here volume means pressure is fixed, and you are increasing the number of molecules, right? You are increasing the number of molecules. So definitely there will be crowding, right? There will be more number of molecules present within it, within a fixed area, right? So the volume will be decreased, right? So if volume decreases, then it will be proceeding again towards the region where it can minimize the effect, right? Where it can minimize the effect. So definitely it will proceed through, you can see it will proceed through the product direction. Okay, I guess it's clear. Let's proceed for the next case. Okay, here you can see NH3 is a Lewis base and BCl3 is a Lewis acid. You have to explain. So definitely you can see nitrogen is having a lone pair and it donates the lone pair. And as it has extra lone pair to be donated, and hence you can call it Lewis base. And BCl3, boron is electropositive in nature. It can accept electron. So this lone pair can be donated, and this boron, it accepts lone pair. So as it accepts lone pair, then you can tell that it's a Lewis acid. Okay, next you can see state and explain the law of mass action. So the law of mass action, it's a statement, it's a direct question. You can simply just write it down. So you can see the law of mass action states that the rate of a chemical reaction is directly proportional to the product of the active mass of the reactant, each raised to the power of its stoichiometric coefficient. Means if I simply write the reaction, let's say small a of A plus small b of B gives me small c of C plus small d of D. So if I want to write the rate is directly proportional to the concentration of the reactant raised to the power of the stoichiometry, like this. Okay, now if you just remove the constant, so this is for the forward reaction. Okay, this is the forward reaction. Now if you remove the proportionality sign, there will come a constant that is called the rate constant. So here you can see, here rate constant I am explaining for the forward direction, that's why Kf I am writing. So it should be A power A into B power B. So here also after writing this, you have to explain this. Along with that, please mention the abbreviation. This is the rate of the forward reaction. What is Kf? Kf is the rate constant for the forward reaction. A is the active mass of A, B is the active mass of B. Okay, small a is the stoichiometry of A and small b is the stoichiometry of B. That you have to mention after writing this. Okay, don't forget to write the abbreviation. It means a lot. Otherwise, there should not be any question. Like whenever your answer, there should be the answer in your copy. No, it should be fulfilled, right? So now you can see derive the relationship between Kp and Kc. Okay, so let's write it here. See, for this reaction, I'm just normal reaction, I'm taking small a of A plus small b of B will give me small c of C plus small d of D, right? If I write the Kc for this, it should be C power C D power D divided by A power A into B power B. Let's say this is my equation number 1. Okay, so now you can see I know from ideal gas equation PV equals to nRT. From here I can write P equals to N by VRT. Hence I can write from here P equals to CRT, concentration into RT. Okay, so now let's write pressure of A, pressure of B, partial pressure of C. These are the partial pressure, okay, and partial pressure of D. So partial pressure of A should be the concentration of A into RT. This should be the concentration of B into RT. This should be the concentration of C into RT. And here it should be the concentration of D into RT. Okay, let me erase this portion. If you write Kp, here it comes partial pressure of C power C, partial pressure of D power D divided by partial pressure of A power A, partial pressure of B power B. Let's put these values here. Okay, so from here Kp is something like, I am having this thing, C into RT power C. Here I am having concentration of D into RT power D divided by concentration of A into RT power A, concentration of B into RT power B, right? Now from here just a little bit simplification I am proceeding with. Kp should be equals to C power C into D power D into A power A. Here comes B power B, and here RT power, overall I am writing together C plus D minus A plus B, right? These are the things coming, right? So from here, this thing I don't have to tell you, this is nothing but the Kc. So Kp equals to Kc into RT power this entire thing. Now let me tell you, this particular thing is called del N. So what is del N? Del N is basically equals to stoichiometry of product, gaseous product. Please remember, gaseous product minus stoichiometry of the reactant. Gaseous reactant only you have to consider. Okay, so RT power del N. Fine. So this is going to be the relation between Kp and Kc. Okay, I guess you understood this, or you will get the direct derivation in the NCERT as well, so you can do it like that. Let's proceed further. Okay, so Le Chatelier principle and what is the effect of temperature and pressure on equilibrium. Okay, so first pressure I already explained, you can just proceed with the same thing, like pressure is what? If you increase the pressure, that it will be proceed towards that direction of the equilibrium where there are lesser number of molecules. That's it. Okay, so now Le Chatelier principle, just go through. This is the statement given over here, means any disruption if it created, means if pressure is increased or volume is disturbed or any kind of temperature increase or decrease, this type of thing if you see, then the equilibrium will try to adjust its effect, this type of effect, and it tries to minimize the disruption. It always tries to attain the equilibrium state. Okay, so this is the Le Chatelier principle. Okay, now effect of temperature I can explain in two cases, exo and endo. Exo means temperature is released and endo means temperature is absorbed. Okay, both the cases, if I increase the temperature, that effect I will tell you. If you increase the temperature, what will happen to the exothermic reaction and what will happen to the endothermic reaction. Okay, so if you increase the temperature in exothermic reaction, this thing already I explained to you. Exothermic reaction means it releases heat, right? It gives heat. So once it gives heat, so if you increase the temperature further, it will be causing disruption, right? So any process, if forward is exothermic, backward is endothermic. So definitely endothermic is heat consuming, temperature consuming, right? So if you increase the temperature, it will try to utilize the temperature, hence it will proceed towards the backward direction. Okay, so for the exothermic case, if you increase temperature, backward reaction will be favored. Okay, now if you are having endothermic reaction, in endothermic means it takes heat, so definitely it takes heat, it requires heat to proceed, and you are giving heat, you are increasing temperature, so it will nicely proceed towards the forward direction. Right, again if I decrease temperature, okay, for exo, for endo, see, for exo we don't need any heat and you are decreasing the temperature as well, right? So definitely it will proceed for the forward direction. That is, whenever your temperature decreasing, it will proceed towards the forward direction. And endothermic requires temperature and you are decreasing it. Okay, so forward step is endo, backward step is exo, right? So definitely it will proceed towards the backward direction, just opposite, you can see. Okay, always remember the temperature that you are giving or you are taking, that it will try to utilize to minimize the effect of the temperature. That's it. Okay, let's proceed. Here I am coming up with the numerical problems, so one by one let's solve. Okay, okay, so the first one, you can see the reaction between N2 and H2 to form ammonia has Kc value. Okay, so Kp you have to find out. So definitely here nothing you have to do, simply P-Kc relation you have to apply. So what is the relation? Just now we derived Kp equals to Kc into RT power del N, right? So here simply Kp I have to find out, right? Kc is given, Kc value let's put 6 into 10 power minus 2. Okay, now let's write the R value. R is 8.314. into 500 degrees Celsius. If you convert it into Kelvin, it's going to be 773. Okay, del N let's calculate. So what was del N? Stoichiometry of product minus reactant. So the reaction between N2 and H2, you know, N2 plus H2, 3H2 will give you 2NH3, right? So it's going to be 2 minus 3 plus 1, 3 plus 1, 4. So 2 minus 4. So you are going to get 2. Okay, so here you are going to get minus 2. So definitely the power is going to be minus 2. So if you calculate this entire thing, your Kp value will come around 1.452 into 10 power minus 9. So that is your answer. Okay, I guess you understood. It's a direct question, direct, you just put the formula and you will get it. Let's proceed further. Standard gives free energy change for the reaction is given. Calculate the Kp. Okay, there is a direct relation among del G, means gives free energy, and P that we are going to use here, that is del G equals to, these are the question zone mainly from where actually the numerical problem comes. First one is definitely that Kp Kc relation, the second one is that del G and Kp relation, and one more we will proceed with. Okay, so del G equals to, you can see, minus 2.303 log Kp. Fine. So from here I can put log Kp value. Log Kp is going to be, del G value let's put 173.1. It's kilojoule value. Okay, let's convert it to joule, into 10 cube joule divided by 2.303. okay, one negative sign was also there, 2.303 into R value is 8.314 into 298 Kelvin. Okay, yeah. So now if you calculate this, log Kp will come something around 30.33. Now if you proceed with the Kp, that should be 10 power 30.33, that is equals to, that is almost equals to 2.11 into 10 power 30. Okay, so that's gonna be the answer. Okay, let's proceed. I guess you understood this. It's also a direct questions, direct formula apply. Okay, let's proceed for the next one. Okay, so here comes a question, calculate the del G0 and Kp for the following reaction at 298 Kelvin. This is the reaction. Del G0 value for the formation for these things are given. Okay. So let's find the del G of reaction. Okay, del G for reaction, always you remember summation of the del G0 of product minus summation of the del G0 of the reactant. Okay, so what are the product? CO2 and H2. So simply just put the value. Okay, so what is the value of CO2? Okay, for Ca2 minus 97.26, right? Minus 97.26. Okay, plus hydrogen gas, that should be 0. Okay, next here should come one minus sign, and let's proceed with the further. That is the reactants. It should be minus 32.807, I guess, yeah, minus 32.807 plus plus this value minus of 54.64. okay, so now if you calculate this entire thing, your value will come around minus 119.1 kilojoule. okay, your value will come around like this. Fine. Then let's proceed for the next step. Then you know already the last thing that we did here, del G0 equals to minus 2.303 RT log Kp, right? So del G0 you got, it is a one part of the reaction, and then you have to find out the Kp. So log Kp is something going to be del G0 divided by minus, one minus sign will come, 2.303 RT. Now simply just put the value and do the calculation. So if I put the value here, minus 119.1 kilojoule divided by 2.303 into 8.314 into 298 Kelvin. Okay, so almost the value will come as, the value will come almost 20.84. Fine. Now Kp, how you should consider? Kp equals to 10 power 20.84. okay, so if you calculate this, Kp should be equals to 7.315 into 10 power 20. okay, so that's gonna be the answer for this problem. okay, so let's proceed for the next one. okay, so pH of sample of milk is 6.4. calculate the H plus, concentration of H plus. So simply just anti-log you have to do, you have to proceed with this, like pH you have to break down, minus log of concentration of H plus equals to 6.4. From here you can write concentration of H plus equals to 10 power minus 6.4. okay, concentration of H plus, from here you can get, it will come something like 0.39 into 10 power minus 6 molar. I guess you understood this. Let's proceed further. okay, so here you can see the solubility of BaSO4 is given at particular temperature. Calculate the solubility product. okay, so BaSO4, if you dissociate, it's a sparingly soluble salt, right? If you dissociate, it will come as Ba2 plus SO4 2 minus, right? So it will give S, it will give S. So Ksp value should be A square, right? Now here one tendency comes, you directly put the value of 2.33 into 10 power 4. Don't do this. Molar solubility you have to mention here. So how to find out the molar solubility? So solubility is given something like, see, it is gram per ml. Fine, it's gram per ml. So from here I can write solubility equals to 2.33 into 10 power 4, right? 10 power 4 gram per ml. So from here I can write 2.33 into 10 power 4 divided by 233. 233 is the molecular weight of BaSO4 into 1 by 10 power minus 3. Okay, minus 3 liter, right? So now you can see from here, actually I am getting the value 0.01 into power 0.01 into 10 power 4 into 10 power minus 3. From here, if you simplify it, you will get 1 into 10 power 5 mole per liter. Right, this value now you have to apply for this equation. So now you put KSP value. Now you put KSP value as 1 into 10 power 5 mole per liter whole square. So definitely if you do it, that is 10 power 10 mole per liter. Okay. So if the value is given as gram per ml, please don't forget to consider as like molar solubility. Take it into the mole per liter unit. Okay. I guess you understood this. Let's proceed further. Okay. So find the pH of a buffer solution containing 0.20 mole per liter CH3CAA and 0.15 mole per liter CH3COH. K for the acetic acid is given. Okay, so for this case, definitely there is a equation, I guess you people know, it's called Henderson-Hasselbalch equation that you have to apply. So pH equals to pKa plus log salt by acid. Okay, so now what you have to do, now just simply put the value. Okay, so we also need to find out the pKa as well from here, because Ka value is only given. So pKa means minus log of Ka. Okay, simply just put the value, or simply just put the value by putting like I can write log 1 by Ka, right? So log of 1 by 1.8 into 10 power minus 5. Fine. So if you calculate this particular thing, your answer will be something around 4.74, something around this. So to know even detail that how you should calculate the log, there will be a different video that will come very soon that will explain all the tips and tricks that is required to solve the numerical problem. Okay, means whenever you are having the log, very difficult value like this critical value, how you should analyze those things, that will come in a separate video. Okay, so that you have to watch. Okay, so as of now, just I'm writing the values only. Okay, so 4.74, that is a value, it will come here. Now what to do? Now just directly put it here. pH equals to 4.74 plus log of, now put the value from the question. One is 0.20, another one is 0.15. Okay, so this is 0.15 and this is 0.2. Right? Yes. So now if you just calculate the entire thing, it should be 4.74 plus, if you calculate log of 0.75, it will come from here. If you further calculate, pH will come as 4.74 minus 0.1249, this thing. Okay, log 0.75. So for this further, pH should be something like 4.6198. This is going to be the pH. Okay, I guess this thing is clear to you. Just simple you have to add the you have to apply Henderson-Hasselbalch equation, and then simply you have to put the values over here. Okay, and then calculation. So calculation in the board case, you will get the log table, but in case you are facing any problem for the log, that I will help you out in some other video. Okay, so I guess you understood. Okay, I guess you understood what are the question zone, means numerical problem zone for the equilibrium chapter. First numerical, that usually it KP-KC relationship. Second one is that the del G and KP relation, right? And the another one you can see it's from the Buffer Henderson-Hasselbalch's equation. Another one is direct, they can ask the pH, okay, pH calculation, and another thing is solubility product calculation. Okay, so direct formula application, I guess there should not be any problem. These particular zones are very much important for the board purpose. Please focus on them and your entire equilibrium chapter will be shorted. Okay, and also remember that any one of the effect, Le-Chatelier principle statement is definitely, it is important. Law of mass action statement is definitely important, and any one of the effect may come. Okay, temperature, pressure, volume, and addition of inert gas. Okay, these affect, how they affect in the equilibrium condition. Okay, any one of them can come. Okay, majority will discuss. We covered the entire thing. We covered the temperature, we covered the, in temperature also exo and endo, both the cases we covered in these questions. Pressure also, and that effect of helium gas, decreasing volume, everything we covered here. So I guess you understood where actually board people target. Okay, please be focused on the target zone only, then you can get the better marks. Okay, so let's proceed for the next chapter, that is the redox reaction, and we will start with the MCQ at first. So as you can see, first question is, two oxidation state of chlorine are found in the compound that are given below. Okay, so if you just look at one by one compound, here C2O7, KClO3, KCl, everywhere you can see the same oxidation state of the every metal if you count. But if you just look at that CaOCl2, okay, hypochlorite type of compound, here you can see two different type of oxidation state is exhibited by chlorine. So for this particular case, let me show you. It is basically CaOCl minus and Cl minus, they exist in this form. Okay, this OCl minus, this particular unit is called hypochlorite. Right, so from this particular portion if I calculate OCl minus, so for oxygen it is -2, for chlorine it's unknown, equals to -1. So from here x equals to -1 plus 2, from here I am getting x equals to +1. Okay, so you can see chlorine here is +1 and this particular chlorine it is -1. So two different type of oxidation state of chlorine is observed over here. So this is going to be the correct answer. Okay, so let's proceed. Here you can see CrO5. CrO5, if you do in general method like CrO5, if I want to find out the oxidation state of chromium, and then I'm taking it as X, and here for oxygen this is -2 into 5 equals to 0. So for this case you can see X is coming +10. So +10 oxidation state is not possible actually. So here oxidation state maximum can go up to +7. Okay, so whenever you will see that after that it is coming after +7 it is coming, then feel that there must be some peroxide type of linkage where oxygen exists in -1 oxidation state. So let me just draw the structure of CrO5. This is a CrO5 structure, and here you can see this is one peroxide linkage and this is one peroxide linkage. So these two oxygen exist here, these two, and there these two oxygen, total 4 oxygen exist as a peroxide. So how actually you should write? So this is not the correct way. You should write X plus 4 into -1 plus 1 oxygen of -2, right, equals to 0. So from here if you calculate x minus 4 minus 2 equals to 0. So from here you can see x equals to plus 6. Okay, so plus 6 is going to be the correct answer. Okay, let's proceed for the next one. You can see which of the best description of the behavior of bromine in the reaction given below. Okay, so here you can see H2O plus Br2, it's giving HOBr and HBr. So Br2 here it is oxidation state 0, but if you calculate this case, let's calculate once. HOBr, here it is plus 1, oxygen is minus 2, and bromine is, let's say, x equals to 0. From here I am getting minus 1 plus x equals to 0, hence x is coming as plus 1, right? So here bromine is in plus 1 oxidation state and here bromine is in minus 1 oxidation state. So bromine here it is getting oxidized, right, because it is losing electron, right, and from here to here it is getting reduced, hence it is gaining 1 electron. From 0 to minus 1 it is gaining electron, right? So it is oxidized and reduced simultaneously, hence you can see it's a disproportionation type of reaction, and your correct answer is going to be option B. I guess you understood this. Let's proceed further. Okay, so find the oxidation number of the highlighted element in each of the following. Okay, so let me just find out for H2S4O6. So for this particular case I am taking H as a plus 1, so plus 1 into 2 plus sulfur I have to find out, right? 4x plus 6 into minus 2 equals to 0, right? So from here I am getting 2 plus 4x minus 12 equals to 0. From here I am getting 4x equals to 12 minus 2. So from here I am getting x equals to 10 by 4, right? So from here I am getting 2.5. Okay, fractional oxidation state. So here actually what happens, it exists in this type of structure. It exists in this type of structure. Fine. So now if you want to find out, here different sulfur has different oxidation state. So how you should find out? You should always avoid the sulfur-sulfur linkage, right? So you can see here sulfur-sulfur linkage, how many sulfur-sulfur bonds are there? Here I am having 2 sulfur-sulfur bond, right? So that's the reason here that I will neglect, and but here if you just see 1 sulfur-sulfur bond and rest of the bond 1, 2, 3, 4, 5, 6. Here I am having plus 6. So here different type of oxidation state for sulfur is observed, and that's why you can see different oxidation number. I mean to say the average oxidation number actually comes. So whenever they will ask you to find out, you can write this thing. Okay, 2.5. Okay, next I can proceed with K2Cr2O7. So here you can see here how you should proceed. Okay, let me just take a fresh page. So here I am having K2Cr2O7. For this particular case, 2 into plus 1 plus chromium I have to find out here. So here 2 into x plus 7 into minus 2 equals to 0, right? From here x you will get plus 6. Okay, so like that you can proceed with the oxidation number calculation. Let's proceed with the next one. Using the stock notation, represent the following compounds. Stock notation is nothing, just whatever the oxidation state will come, that you have to write it in a bracket just beside the metal present over here. Okay, so HAuCl4, if you just write HAuCl4, if you just write from hydrogen plus 1, gold I don't know, so X I have to take. Along with that, 4 chlorine is of -1 equals to 0. From here +1 plus X minus 4 equals to 0. From here I am getting X equals to 4 minus 1. Hence X I am getting 3. Right? So simply you have to represent it like this. Okay? And here again if you write Fe2O3, so here normally by looking at the compound itself you are understanding that iron is in +3 oxidation state, right? So here also you can write it Fe2, here you can write 3O3 like that. This is your stock notation. Okay, so let's proceed for the next one. So here what I have to do, I have to balance this compound by half reaction method. Okay, so half reaction method, it is in the acidic medium. There are several steps I can show you, and please try to attempt this type of question because it will give you the complete full marks. And don't forget to show each and every steps, because let's say in the last step you are making some mistake, you will get the step marks. Okay, so first you have to split the reaction into two half reactions. So Fe2 plus is getting converted to Fe3 plus, and another part is Cr2O7 2 minus is getting converted to Cr3 plus. Okay, so first what you have to do, balance any atom rather than oxygen and hydrogen. Okay, so first you can see iron 1 both the side it is same, it is fixed, you don't have to balance anything. But you can see chromium this side 2, this side 1, so this side you have to multiply with 2. Okay, now after balancing the other atom, proceed for the oxygen. How you should proceed for the oxygen? So you are having, wherever you are having lack of oxygen, there you have to add oxygen in terms of water. Okay, whatever the amount of lagging are there, let's say here I am having 7 oxygen, there no oxygen, so 7 water I have to add. So if I add 7 water here, by default you can see hydrogen comes. So hydrogen balance you should do at the opposite side by adding same number of H plus. You can see how many hydrogens are coming, total 14 hydrogens are coming, right? So total 14 H plus you have to add. Right, so 14 H plus you have to add. So now every atoms are balanced more or less. Now my suggestion, like whenever you are proceeding for the charge balance, at first do the easy one. So among these seems easier, right? So only you can add electron, you can't remove, you can't subtract electron from the system, only you can add electron in order to balance the reaction, right? So here +2, here +3, so this side if I add 1 electron, so you can see 3 minus 1 2, so both side now it is 2 2. Right? So now once you are just done with the easy reaction, for the difficult reaction by default be assured that electron will be added in the opposite side. If here first reaction electron is added in the right side, for the next reaction electron will be added at the left side. Right? So for this case, let's count the total charge here. Here I am having +14 minus 2, hence I am getting 12, right? And here also I am having +6, because +3 each chromium, I am having 2 chromium. So +12 I have to take it to +6. So I can add 6 electron here. Right? So this is how you can see. Now charge balance is done. Now charge balance is done. Now what you have to do? Now you have to make the electron number equal before you are adding it. So let's say this is my equation number 1 and this is my equation number 2. So equation 1 I am multiplying with 6. So if I multiply equation 1 with 6, it will be something like 6 Fe2 plus will give you 6 Fe3 plus 6 electron. Why I am doing it? Just in order to cancel out the electron. See, electron we don't get it from the market, right? That in the reaction I am adding 1 spoon of electron or 1 gram of electron. No, na. So why we are taking the electron here? Just electron help me to balance the charge, right? Once the charge is getting balanced, then there is no role of electron, you can remove it. So in order to cancel out the electron, you have to make the number of electron in the both reaction equal so that you can cancel it out, right? So next I am adding this equation with the second one. Okay, so let's write the second one. Cr2O7 2 minus plus 14H plus 6 electron. That side 2Cr3 plus 7H2O. Okay, so now you can see both sides 6 electron gets cancelled out. Now write the overall thing. 6 Fe2 plus Cr2O7 2 minus plus 14H plus will give you 6 Fe3 plus 2Cr3 plus 7H2. So this is your balanced equation. Okay, so this is your balanced equation. This is how you should balance it. I guess you understood this. Please make sure while you are watching the video, make sure you are writing it, because always I keep telling you, pen and paper is your main weapon to crack any examination or develop a concept. Okay, once you are holding your pen while writing the entire concept while learning, your concept will be in your grip. Okay, so make sure you are writing simultaneously while watching. Okay, let's proceed for the next one. Okay, so here we can start for the hydrocarbon chapter. Okay, so here you can see very basic questions actually comes from the hydrocarbon, not that much difficult or that much hectic, because conversion and all type of name reaction you are going to expect in 12th itself, means your PO2 itself. So as of now, very simple type of reaction only, it will come in your board exam, and straightforward reaction you can expect. So I will tell you what are the main focused zone in the board, that you listen, watch till the end, you can understand. Okay, so which of the following reaction is used to increase the length of the carbon chain? Okay, so length of the carbon chain means, let's say I am having 2 carbon in my system, I will be having more than 2 carbon after the reaction will be taking place, right? So this is called step up process. Step up means whatever the carbon number initially, now the number has increased. It's a step up process, right? So first you can see, look at the reagent, Wolff-Kishner's reagent, Wolff-Kishner's reduction, it's a reduction reaction. Okay, it's a reduction reaction. So it has nothing to do with the carbon itself. What it does, it adds some hydrogen. Okay, so it has no role in increasing the number of carbon. Fine. Clemmensen reduction, it is also a reduction reaction, right? So it is also having no role in increasing or decreasing the number of carbon, rather it helps in the maintaining the hydrogen number, right? Now Cole's electrolysis, let me tell you my dear, it's a step down process. What happens, 1 carbon gets eliminated from the system in the form of carbon dioxide. Okay, so Cole's electrolysis process is also not going to be the correct one. Okay, now look at the system, Wood's reaction. So Wood's reaction was what? I guess you remember, you are having alkyl halide, let's say I am having methyl chloride and sodium in dry ether. That was the reagent for it. So the reaction, 2 unit of sodium, actually you need, let me write another ClCH3. Okay, so NaCl and NaCl will be eliminated from the system, and CH3 will make the bond among themselves, CH3. So I started with a single carbon system, that is the methyl chloride. Okay, I had 1 carbon system, but now I am having a 2 carbon system, right? So you can see the number of carbon will increase, hence Wood's reaction is going to be the correct one. Okay, let's proceed. Okay, in the combustion of alkanes, if ethane is used, how many moles of oxygen are required here? So for this particular case, let me show you the reaction. So I am using ethane, right, means C2H6. So I am using C2H6 here. C2H6, sorry. C2H6 will use some amount of oxygen, and during combustion, complete combustion, it forms CO2 plus 6H2, right? So now what you have to do, you have to simply balance it, right? So if I balance it, it will come as sorry 6H2. Okay, he will be having 6H2. Okay, so now I guess you understood the answer. Your answer is going to be the 7. Okay, so let's proceed for the next one. So here I am having a system. You can see, if you are having a system something like that, Cn H2n plus 2, right? So this is the alkane system I am having. N is the number of carbon atom, right? So that N value comes here, okay, and here it comes 3n plus 1 amount of oxygen, okay, and here in order to get the CO2, I usually get 2n amount of CO2, and here you will end up with similar number of hydrogen, means here total overall I am having 3n, so 3n number of H2. This is a in general rule that you can proceed with, okay. So this is a in general rule to balance the alkane, okay. So you can proceed, you can remember this formula and you can proceed with the balancing process, okay. Let's proceed further. Here you can see ethyne on oxidation with KMnO4 forms hydrochloric acid, oxalic acid, acetic acid and formic acid, okay. So I am having ethyne means this type of system, right? So whenever I am using the alcoholic KMnO4, it's a very strong oxidizing agent, so it entirely, okay, sorry, so it entirely oxidizes the system to oxalic acid. So if I just write it properly, I will get something like a 2-carbon system, but both the carbon will be oxidized. So you will get COOH attached with another COOH. Okay, this carbon and this carbon both will be oxidized, and the maximum oxidation, I guess you know, it is for the carboxylic acid. So 2-carbon system, hence 2 carboxylic acid unit, they are attached to each other. Hence this is my oxalic acid. Okay, let's proceed for the next one. Here you can see, calculate the number of sigma and pi bonds present in benzene. So if you just simply draw the structure of benzene, let me just draw it like that so that you can understand the pi bond and all the sigma bond easily. So this is my benzene, this is how it looks like. Now count the sigma bond. So here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm having 12 sigma bond and 1, 2, 3 pi bond. So option D is going to be the correct one. Okay, I guess you understood this. Let's proceed for the next one. Okay, which of the following is used to reduce the phenol vapors to benzene? Okay, so for this particular case, you can see I am having hydrogen gas, I am having oleum. It's a direct question actually. If you know the reaction, then you can do it. So let me tell you, from phenol to benzene we can go for direct conversion by using the zinc dust. Let's proceed for the next question. You can see the question: benzene on treatment with excess chlorine in presence of anhydrous LCl3 under dark and cold condition. Okay, so normally here what happens, if any 1 unit of chlorine if you use, in this case you will get normal chlorobenzene, but they are saying that excess chlorine and you are doing this reaction in a dark and cold condition, hence all the hydrogen of the benzene ring will be substituted with the chlorine and you will get this type of system. You will end up with this type of system. Okay, so this is called hexachlorobenzene. Okay, all the hydrogen of the benzene ring will be substituted with the chlorine, hence you will end up with the hexachlorobenzene. Let's proceed with the next one. Here you are having illustrate the conversion of propane to propane. Okay, it's a simple reaction, just simple, you do nickel hydrogenation and you will end up with the propane. Okay, propane means you are having something like CH3, C, triple bond, CH, this type of system. This is your propane. So simple, you do H2 in presence of either nickel or palladium or platinum. Okay, and you will end up with this propane. Okay, as simple as that. So simple nickel hydrogenation. I guess you understood this. Let's proceed for the next one. Explain Wood's reaction with an example. Okay, so Wood's reaction means when it's a step up process, I already told you, and it's a zone, board alert zone, highly board alert zone. Please be careful. Each and every year more or less I can see that the questions are coming from the Wood's reaction either in the MCQ or in the 1 marker, 2 marker type of question. Okay, so simply if you just start with the methyl chloride example. Okay, so 2 unit of methyl chloride you have to take. You are taking sodium, 2 unit of sodium in dry ether. 2 unit of sodium in dry ether, and you will end up with CH3. Along with that you will end up with 2 unit of NaCl. Okay, so this is your actually Wood's reaction. So how basically it happens, it's a dimerization process you can say. So not dimerization, basically chlorine is getting eliminated, 2 alkyl unit they get dimerized. Okay, plus here you can write sodium, plus sodium here you can write. You don't have to proceed for the mechanism, just simply show the reaction, it will give you the full marks. So from here 1 unit of sodium chloride, from there 1 unit of sodium chloride will be gone, and from here you will end up with CH3, right? So you will end up with ethane. So that if you write, you will get the complete 2 marks. Okay, so let's proceed with the next one. So what is a pyrolysis? Write the chemical equation supporting it. Okay, let's proceed with the next question. You can see what is pyrolysis, write the chemical equation supporting it. Okay, so pyrolysis is nothing but the breaking down of one alkane chain while it is heating. So you can say that it's a simple decomposition type of reaction. Okay, so simply let's say I am taking C6H14. Okay, so simply what as a definition what you can write, so higher alkanes on being heated it gets converted to a smaller compound, smaller alkanes. Okay, so that process is called pyrolysis. Okay, so here you can see if this particular system I heat, okay, high heat, let's say 773 Kelvin temperature. Anyway, you just have to heat the system, then I can get C6H12 along with 1 hydrogen. Okay, I can have
C4H8 and C2H6 type of compound. Okay, from here also I can get another compound like C3H6. Along with that, let's say I'm having CH4. Along with that, like this type of thing I can get. Okay, just check the balance. Number of carbon and hydrogen should be similar. You can see carbon here 3 plus 1 4 and 2 6, C6. Okay, and hydrogen is also should be 14 altogether. 6 plus 4 10 plus 4 14. Like that you have to proceed for the reaction. This is the pyrolysis. Okay, let's proceed with the next question, that is explain the aromatization of N-hexane. Okay, so let's say you are having N-hexane. So N-hexane, I'm just writing it in this way. I'm writing it in this way, right? It's a chain-like system. Right, now let's proceed with the aromatization. So first you have to give either Cr2O3 type of compound or V2O5 type of compound. Okay, so then this entire ring, this chain cycle, this chain structure gets cyclized. Okay, so you will get a 6-membered ring. Okay, that is the cyclohexane. From N-hexane you will get the cyclohexane. Now further, if you heat the system, almost it is probably 873 Kelvin. If you heat this system further, then this particular thing again it will eliminate some amount of hydrogen and it will aromatize. So once it will aromatize, it will end with benzene. Okay, so this is the process of the aromatization. So definitely you have to start with a chain of the hexane, right? So if you give Cr2O3 or V2O5 type of thing, a little bit heat, maybe you have to give heat. Why? Because a little amount here, two hydrogen needs to be removed to get cyclized. Then after cyclization again you heat the system and you will end with the aromatic benzene ring. Okay, this is your aromatization. Okay, let's proceed with the next question. Now you can see Sawhorse projection of the ethane. Okay, Sawhorse projection means, I guess you know, this particular thing represent the two carbon system, ethane, right? So if I write ethane, it will be something like this. These projections are nothing but the 3D representation of any molecule. So these particular bond represent the bond between carbon 1 and carbon 2. So here I am having, let's say, 2 hydrogen at the top and 1 hydrogen at the bottom. Okay, here also I am doing the same structure, 2 hydrogen at the top, 1 hydrogen at the bottom, right? As you can see, if you just see, this is the particular bond between here 1 carbon, here 1 carbon. So 2 hydrogen top and 1 hydrogen below, right? And here also 2 hydrogen top, 1 hydrogen below, right? So all the hydrogen, they are facing each other, they are eclipsing each other. So this particular form is called eclipsed. Okay, another case, if I just draw when 2 hydrogen, they are actually reverse of each other. Okay, you can see there is no interaction, they are facing. Okay, this particular form is called staggered. Okay, so when they are asking you to draw the projection, my suggestion is to go for both the structure, one eclipsed, one staggered. Okay, I guess you understood this. Let's proceed for the next one. Okay, so here any one you can expect, either the Sawhorse one or the Newman one. So Newman, what we do, we simply imagine the carbon 1 and carbon 2 bond as a cylinder, right? The front, if you just look at the front part of a cylinder, there exists 1 carbon. So let's draw the hydrogen over here, hydrogen, hydrogen and below 1 hydrogen. So backside carbon is not possible to be seen, right? So only the hands projected from the hydrogen that can be seen. Hands projected from the carbon, that can be observed. So this is your Newman projection. So this is again, you can see hydrogen, they are eclipsing each other, right? So once they are eclipsing, you can call the structure simply as eclipsed. Okay, and another form if you want to write, here you are having one hydrogen, here also hydrogen. So all the hydrogens are equally visible here. So this particular structure you can name as staggered. Okay, I guess you understood this. Let's proceed for the next. Okay, so here you can see it's a very common question, important question as well, that state the Markovnikov rule. They directly ask it. So please ensure that you are studying the statement. What is Markovnikov rule? So what happens basically, you are unsymmetrical alkene you are having in your system. So the negative part of the reagent, let's say I'm having the HBr. What is the negative part? Br is the negative part. So where the Br will be added? Br will be added to the carbon that contains less number of hydrogen. Right? So you can see negative part of the reagent gets attached to that carbon of the double bond which carries the less number of hydrogen. Atom. So here one example it's also given. You can see this is one alkene I'm having, HBr I'm having. So Br is getting attached. This particular carbon, these two carbons are containing the double bond. They are holding the double bond, right? So in between these two, which one is having the less number of hydrogen? Definitely this one. So bromine will be attached to this carbon and this carbon will get another hydrogen. You can see bromine is attached here and here another hydrogen. So this is going to be the major product. Another possibility is also there. Bromine can be attached here and here I am getting hydrogen. That will be the minor one. Okay, that is the Markovnikov rule. Okay, I guess you understood this. Please remember that you are going through the statement, and it's very important that like every year more or less that Markovnikov rule statement that you have to write mandatorily. Okay, so please ensure that you are writing it with an example. Okay, let's proceed for the next one. Okay, so explain the mechanism of the nitration of methane. Okay, so now mechanism of chlorination in methane. It is also a very important 3-marker question. Okay, it happens in 3 steps. Okay, initiation, propagation and termination. So in initiation what happens? Chlorine and chlorine, if you just keep it in H nu means in sunlight, the chlorine bond gets splitted in a homolytic fashion. Homolytic means these one electron they takes each. Okay, so you will end up with 2 chlorine radical. That is the initiation. Okay, so once I am having 1 radical in my medium, then any compound, any covalent bond, they will also break down in radical. It's a rule, you can say. Okay, so another thing what I'm having methane. So let's just split the bond so that you can understand. So with any one hydrogen, the Cl dot will approach and it will insist the carbon hydrogen bond to be broken in the homolytic manner as well. So if this bond also breaks down in this manner, so from here what I'm getting, I will get CH3 dot plus 1 H dot plus 1 Cl dot. So Cl dot and H dot, they will combine to give you the HCl, and from here I am getting one CH3 dot. Right? So now what happens? This CH3 dot further reacts with another Cl dot and they gives us CH3Cl. So up to this is called the propagation of the reaction. Okay, you can see this is the propagation of the reaction. Fine. Now you can see here after that the entire thing gets connected and that gets terminated. So I in my media I may have several CH3 dot and they will react with excess Cl dot and they will end up with the excess methyl chloride as well, or else this CH3 dot, it can attach with another CH3 dot as well, okay, and they can give me ethane as a byproduct as well. So this is a byproduct, this is not the major product. Okay, so these are the things that actually happens. This is my initiation, this is my propagation, and this is going to be my termination. Okay, I guess you understood. Here overall things are given, so each and every steps will carry one marks each, so make sure you are just doing it properly. Here hook like arrow you should represent, because it is a single electron transfer. In single electron transfer you should not give double headed arrow, you should use a hook like arrow. Always remember that. Let's proceed. Okay, so here comes the end. So we already have discussed all the important question and all the important board alert zone for the thing. So let me just revise all together. First, from the equilibrium chapter, if you just look at from the equilibrium chapter, I told you Le Chatelier principle is very important, and the statement itself is very important. These are the direct question you can expect, and any one of the effect, temperature, pressure, addition of the inert gas and the volume, okay, any one of the effect you can expect from there. From the conjugate acid base you can expect some MCQ, okay, and for the numerical zone Kp-Kc relation you have to study. From the Kp-Kc relation you can get the numerical problem as well. Delta G Kp relation, it's important, and Henderson-Hasselbalch equation, from there you can find out the buffer. Okay, these are the important question zone. Solubility is also important over there, so we already focused on them. Okay, and from the redox chapter, major two things you can expect from there. One is oxidation number finding out, and another one is balancing. So if you have the proper grip on these two particular part, you don't have any issue, you can sort out the redox reaction properly. Okay, please make sure one of the question you have to attempt, like where you have to balance the entire reaction either in the acidic medium or in the basic medium. Okay, you can expect one of the question, it's a mandatory one. Okay, and please make sure that you are writing all the steps individually. Fine. And another one you can see from the hydrocarbon. From the hydrocarbon, Wood's reaction is a very important one. Cole's synthesis, Cole's electrolysis, I wanted to say. Cole's electrolysis is one of the important reaction from where you can expect some question. Hydrogenation reaction. Okay, another few zones are there from where the question detailed question I will give you in another video. That is the Lindlar's catalyst. Okay, so this type of thing, beta elimination. From there actually the question usually comes for this hydrocarbon chapter. Okay, and few direct question like the aromatization, pyrolysis. Okay, direct they will ask you to write down the reaction. Okay, so please remember those things. The reagent you have to remember, so you can proceed with the entire reaction. So I guess it's going to help you to boost up your memory, to learn, and to get a good marks in your upcoming unit test. So all the very best. Please don't forget to like, share and subscribe our channel to get more such informative videos. Thank you.